Okay, so, wow, you've really outdone yourself this time. You've sent us so much stuff about river landforms, diagrams and maps, and even real-world examples.
Hopefully it's not too much.
No, this is great.
Good.
It seems like you're really into how rivers shape the world around us.
I am.
From like little tiny potholes to huge canyons.
Yeah, all of it, how it all fits together.
Yeah.
Yeah.
It's clear you're fascinated by like erosion and deposition.
I am, yeah. Those are the two big forces we're talking about when we talk about rivers.
Yeah, so for this deep dive, we're going to figure out not just what these landforms are, but how they're formed.
Like how they get there.
I'm ready to have my mind blown.
All right, good. I like that attitude.
All right.
Let's start at the beginning, where the river begins.
Okay.
High up in the mountains.
Okay.
The upper course, this is where the river's energy is at its peak, carving out those dramatic V-shaped valleys.
So I'm picturing like those steep slopes with the river just slicing right through the middle.
Yeah, like a knife.
It's like a sculptor chiseling away at the rock.
Yeah, exactly. And that fast-flowing water, armed with rocks and sediment, it acts like a chisel carving downwards into the bedrock, and we call that vertical erosion.
And we can actually see this in some of the pictures you sent, right?
Absolutely. If you look at slide 1 and slide 12, you can see those classic V-shaped valleys with their steep sides. And notice how the river isn't always flowing in a straight line.
Yeah.
It seems to be kind of dodging obstacles.
Oh, yeah. Those are the interlocking spurs, right?
You got it.
It looks like the river's playing a game of avoid the hard rock.
That's a great way to put it. When the river encounters harder rock or even deep-rooted soil, it's forced to change direction, creating those interlocking spurs. It's a constant battle between the river's power and the landscape.
And it's not just the river doing all the work, though, right?
You're right.
I'm seeing some other forces at play here.
So weathering plays a huge role. Slide 11 shows how freeze-thaw cycles can weaken the rock plant roots, can also break down the rock. Even temperature changes cause cracks and weaknesses.
So it's like a bunch of things working together to make the rock weaker and then more vulnerable to the river.
Exactly, and that's where mass movement comes in.
Oh, yeah, mass movement.
All that weakened rock and soil eventually gives way, landslides and rock falls.
Right, it's all connected.
Exactly, it all works together.
So we've got this powerful river carving downwards, weakening the valley sides, and mass movement reshaping the landscape. So what other features are created by these forces?
Well, have you ever thought about potholes?
Potholes?
Yeah, they're a pain on the road, but in a river, they tell a fascinating story.
Oh, really? What's so special about river potholes?
Take a look at slides 18 and 19. See those depressions? Those are potholes formed by abrasion.
I have to admit, those look a lot different than the potholes I'm used to seeing on the street.
Right, but it's all about erosion. In a river, turbulent water swirls pebbles around in these depressions, grinding away at the bedrock.
So it's like the river is using these pebbles as tools.
Exactly like sandpaper smoothing out the rock. You can see it in slides 20 and 21.
Wow.
How that grinding action slowly enlarges the potholes over time.
It's amazing how something so small like a pebble can make such a big impact.
It really is. And if you look at slide 22, those pebbles trapped in the pothole, that's evidence of that process. And slide 23 shows how those potholes can actually change the course of the river itself.
So as they get deeper and deeper, they change how the water flows.
Exactly. It can even redirect the river.
It's like this constant back and forth.
It is.
Between the water and the rock.
Yeah, a dance.
Okay, so we've seen how vertical erosion creates these steep valleys, how potholes are formed, and how they can change the river's path. What happens when the river encounters a sudden change in the bedrock?
That's where we get rapids and waterfalls.
Oh, okay.
The real drama.
Yeah, bring on the waterfall.
Let's start with rapids. Imagine a river flowing down a steep slope and encountering alternating bands of hard and soft rock. You can see it in slide 28.
I can practically hear the water rushing.
Yeah, it's quite a sight. And remember differential erosion.
Yeah.
That plays a key role here. The softer rock erodes faster, creating steps in the riverbed.
So the river's flowing over these steps, creating turbulence and rapids?
You got it. And this process on a much larger scale is how canyons are formed.
Wow.
Slide 31 shows the Grand Canyon.
That's amazing.
The Colorado River has carved its way through layer after layer of rock over millions of years.
So from tiny potholes to the Grand Canyon,
it's all connected.
It all comes down to water and erosion.
Exactly.
Okay, now let's talk waterfalls.
Yeah.
How do those dramatic plunges of water form?
Waterfalls are basically rapids on steroids. They form when a river flows over a really resistant layer of rock, creating a sudden drop.
I'm looking at slides 32 and 36, and I see a few key features. The plunge pool at the bottom. The overhang of rock and that undercut area behind the falling water.
You've got a good eye. Those are all part of a waterfall's anatomy, and they're all created by erosion and weathering.
Okay, so walk me through it.
So first, you have less resistant rock at the base, eroding faster than the harder rock on top, creating an overhang.
That makes sense.
The force of the falling water creates a plunge pool at the bottom, and the turbulent water erodes the softer rock behind the waterfall, creating that undercut.
So it's like the waterfall is slowly eating its way upstream.
Exactly. We call that waterfall retreat. Slides 38 and 39 show it well. As the undercutting continues, the overhang collapses, the waterfall moves upstream, and the process repeats.
So it's a slow motion march upstream, carving out the landscape.
Exactly. And we see this in the real world with the Powerscourt waterfall in Ireland. It's shown in slides 44, 45, and 46. It's 100 meters high, formed by the River Dargle, flowing over a combination of hard granite and softer schist.
That's impressive. And as it retreats upstream, it leaves behind a gorge, right?
Gorges are those deep, narrow valleys with steep sides. They're basically the scars left behind by retreating waterfalls. The slide 42 shows the River Tees and High Force waterfall in England. It's a great example.
So the river, over thousands of years, can totally transform the landscape.
It's an amazing force.
So we've seen how waterfalls retreat and leave gorges behind, but are all gorges formed this way?
Not necessarily. They can also form in drier areas with seasonal rains.
Like flash floods.
Exactly. Those sudden, powerful floods can carve out those deep, narrow channels very quickly. Slide 41 shows this process.
So different ways to get the same result.
That's right. Nature is creative.
And sometimes it's a combination of forces, right?
Yeah. Slide 43 shows how tectonic uplift can actually work together with the river's erosion to make even deeper gorges.
It's like a battle.
It is a battle between the Earth's forces pushing up and the river carving down.
So we've explored how the upper course of a river is like a hotbed of landform creation.
Yeah.
But what happens as the river flows downstream?
Right.
How does its energy change, and what new features does it create?
That's a great question. That's where things start to get really interesting as the river matures.
Okay.
And its energy shifts. We see a whole new set of landforms emerge. As we move downstream, it's like the river changes its personality.
Yeah, it's not that youthful, energetic force carving out gorges anymore.
Right. The gradient becomes less steep.
Okay.
So its energy is distributed differently. Instead of just cutting down, it starts to move side to side.
Oh, so it's like it's letting loose a little bit.
Exactly. And that leads to the formation of meanders.
Meanders.
Yeah. Slide 14 shows this concept of sinuosity.
Sinuosity.
It basically measures how bendy the river is.
So the higher the sinuosity, the more the river meanders.
Exactly. And slide 15 really shows the difference between a straight channel and a meandering one. But straight channels are actually pretty rare.
Why is that?
Well, it's because of something called helicoidal flow.
Helicoidal flow.
Yeah, it's this corkscrew motion of water that causes rivers to meander.
Okay, so how does that work?
Imagine the water not just flowing downstream, but also spiraling across the channel.
Spiraling.
Yeah, like a corkscrew. Slide 16 gives you a good visual of this.
So is this swirling motion what pushes the river to erode one bank and deposit sediment on the other, creating those bends?
That's exactly it. And to understand how this happens, we need to talk about the thalweg.
Thalweg?
Yeah, it's the line of fastest flow in the river channel.
Okay.
And it shifts towards the outer bend of a meander, as you can see in slides 16, 52, and 53.
Okay, so the faster flow has more power to erode.
Right, and that creates a steep river cliff on the outer bend.
And on the inside bend, where the flow is slower,
the river deposits its sediment.
Okay.
Creating a point bar. Slide 52 shows this process really well. Erosion on one side, deposition on the other.
It's like the yin and yang of a meandering river.
Exactly, a perfect balance, and this continues over time, leading to those really exaggerated meanders you see in slides 54 and 55.
I'm starting to understand how Oxbow Lakes form.
Oh yeah, how's that?
It's like those meander loops get so big that the river eventually just cuts through the narrow neck, creating a shortcut.
You got it. During a flood, the river might cut through, leaving behind an Oxbow Lake.
It's amazing how dynamic these rivers are.
It really is. They're constantly reshaping themselves.
Okay, so slide 56 shows some of these key features. Can I try to name them?
Go for it.
Okay, so we have the river cliff on the outside of the bend formed by erosion. Then on the inside, we have the point bar created by deposition, and the line of fastest flow where all the action is happening is called the thalweg.
Nailed it. You're a natural.
This is really fascinating.
It is, isn't it, how simple processes create such complex landforms?
So as the river meanders across the landscape,
Yeah.
it's not just creating channels, right?
You're right.
It's also shaping the surrounding landscape, like those floodplains.
Exactly. Slides 58 and 59 show these floodplains areas that have been flooded in the past.
And floodplains are known for their fertile soil, right?
Absolutely. The alluvial soil deposited during floods is rich in nutrients, perfect for farming. It's like the Goldilocks of soil.
So how are they formed? It can't just be the river overflowing its banks, right?
Well, flooding is key, but it's about how the sediment is deposited.
Okay.
When the river overflows, the water slows down and loses energy.
Okay.
So the sediment settles out the heavier particles first closest to the channel.
So that's how levees form.
You got it, those natural embankments along the river banks.
Like the river is creating its own protection system.
That's a great way to think about it. And the bluffs you see in slides 59 and 60 mark the edge of the floodplain.
Okay, so it's like the boundary between the floodplain and the higher ground.
Exactly. It shows how far the river's influence reaches.
It's incredible how the river shapes not just its own channel, but this whole landscape.
It's a powerful force, and as it continues downstream carrying all that sediment, it eventually reaches the sea or a lake.
And that's where deltas form, right? Those triangular landforms named after the Greek letter delta.
You got deltas form at the river mouth where the velocity drops.
So all that sediment the river has carried for miles is deposited here.
Exactly, the grand finale of the river's journey.
It's like a giant fan of sediment spreading out.
But for a delta to form, you need certain conditions.
Like what?
The sea or lake needs to be calm with low tides and weak currents, so the sediment isn't washed away.
It's like the river needs a peaceful ending to its journey.
You could say that, and just like floodplains, the way the sediment is deposited is important.
Okay.
As the velocity drops, the sediment settles out in layers.
I see that in slide 64, the cross-section of a delta.
Right. You have the bottom set beds, the finest sediment carried furthest out, then the foreset beds with medium-sized particles, and finally the top set beds with the coarsest material.
So it's like a sorting machine.
It is nature's sorting machine, and then you have those branching channels spreading across the delta.
Those are the distributaries, right?
Yes, as the delta grows, the sediment can block the river's flow, forcing it to split.
So the river is creating its own network of waterways.
Exactly, and that's what gives deltas their triangular shape.
But I know not all deltas look the same. Some are more rounded, some are pointed, some look like a bird's foot. What causes those differences?
That's a great observation. It depends on things like the river's flow, the tides, the currents, and even the type of sediment.
So it's a combination of the river and the environment?
Exactly. Slide 66 shows examples of the three main types of deltas: arcuate, cuspate, and bird's foot.
Okay, let's see. The Nile Delta is arcuate with a rounded shape. Then the Ebro Delta in Spain is cuspate, more pointed. And the Mississippi Delta is a classic bird's foot.
Those are all great examples. Each delta has its own story.
Okay, let me test my knowledge using slide 70.
Go for it.
Okay, so deltas form when a river meets the sea or lake deposition happens because of the drop in velocity. The finest particles are carried furthest out. The middle layer is the foreset beds. The top set beds are the coarsest, and the smaller channels are distributaries.
You got it all right.
I'm feeling like a delta expert.
You've learned a lot.
So we've journeyed from the energetic upper course to the meandering middle course, and now to the deltas. It's been quite a ride.
It has. What are some key takeaways for you?
I think the main thing is how connected everything is.
I agree.
These landforms aren't isolated, they're part of a continuum.
And it's not just about rocks and water.
Right.
It's about how these natural processes shape our world and how important rivers are for us.
They provide water, fertile land, and transportation.
Exactly. And that brings us to an important question. How might climate change affect these landforms in the future?
That's a big one. Climate change is already changing rainfall and causing more extreme weather. How will that impact rivers?
Well, it's likely to cause more intense floods leading to more erosion and changes in deltas. We might even see rivers changing course more often.
So the balance could be thrown off.
Right. It's a complex issue. Scientists are studying how to adapt and mitigate these impacts. We've come a long way from those mountain headwaters with the gorges and waterfalls.
Yeah, all the way to the deltas where the river meets the sea.
It's amazing how one force of nature can create so many different landscapes.
And it's not just about the scenery, right?
Right.
These landforms are really important for people too.
They are. They're intertwined with human societies.
Yeah, so how does understanding these river landforms actually affect us?
Well, for one, it's crucial for flood management.
Okay.
Knowing where floodplains are likely to form
Yeah,
can help us decide where to build so we don't put structures in vulnerable areas.
that makes sense. Building on a floodplain sounds risky.
It is. And remember those fertile alluvial soils we talked about?
Yeah, the Goldilocks soil.
Exactly. Understanding how those are formed is essential for sustainable agriculture.
It really shows how these processes aren't just happening out there on their own.
Right.
They directly affect our lives, from erosion to fertile soil. The river shapes our world.
It does. It highlights those connections between nature and human activities.
Yeah, and that brings us to a big question. How might climate change impact these river landforms in the future?
That's a crucial question.
Yeah, I know climate change is already messing with rainfall patterns and causing more extreme weather.
Right. More intense floods.
Yeah.
Increased erosion changes in the shape and size of deltas. We might even see rivers changing course more frequently.
Wow, so that balance that the river has maintained for so long could be disrupted.
It could, with unpredictable consequences.
This is complex stuff.
It is. Scientists are working hard to understand how to adapt to these changes.
Well, this has been an eye-opening journey.
It has, hasn't it?
I feel like I have a whole new appreciation for rivers.
And that's what it's all about. The more we understand about these natural processes, the more we appreciate our planet.
You've given us a lot to think about.
Hopefully so.
But here's a final question for you, the listener. What role do rivers play in your local environment? Are there any unique landforms or challenges related to rivers in your community? We encourage you to go out, explore, and learn. Until next time, keep diving deep.